Hi everyone, welcome. The purpose of this video is to go over using delta H of combustion or delta H of formation to find delta H for an overall reaction. These are two theoretical ways to find enthalpy change in a reaction. So what does that mean? That means for some reaction where we have reactants and we have products, we can look up either the delta H of combustion data or the delta H of formation data for each reactant or each product, I should say. So, oops. So the idea is that you get either the delta H combustion data of each of these individual things, and you use that to find the enthalpy change for the overall reaction, or you get the delta H formation for each individual reactant or product molecule you're looking at, and then you can use those, you can combine those to find the enthalpy change for the overall reaction. So let's take a look at what that might look like. So as a reminder, we're going to start with formation. As a reminder, what do we mean by enthalpy of formation? Enthalpy of formation, and really we're using the standard enthalpies of formation, the ones we would find in the data booklet, which you see over here on the right, is the enthalpy change when 1 mole of a compound is formed from its elements. And we know that for any elemental states, delta H of formation is 0. So we're going to look at a couple of examples here. So here's our first example problem. We have C2H4 plus HCl yields C2H5Cl, all in gas form. Okay, so this is just a synthesis reaction. You can have any type of overall reaction. One thing that kind of confuses people is sometimes our overall reaction is itself a combustion reaction or a formation reaction. But what we're trying to do is we don't really care what kind of reaction my overall reaction is. That's the overall reaction. Great. What I need to do with both of these methods is I need to take each thing, each reactant, and each product and get the information for it. So in this case, I'm starting with formation. So I am going to use let me write this down. I'm going to use the delta H formation for each reactant product molecule to find delta H for this overall reaction. To find delta H of reaction. Finding delta H, finding the enthalpy change for a reaction, that should feel familiar. We've seen experimental ways to do this. We've seen using given intermediates with Hess's law. We're now seeing us having to look up the intermediates using delta H of formation. So I'm going to look at each of my things. I have C2H4. What would the formation of C2H4 look like? Well, I would need 2 carbon atoms plus 2 hydrogens. Remember, hydrogen is diatomic, making C2H4. The delta H of that, let me make some space here. I'm just going to look that up. This delta H is going to be, the delta H of formation for C2H4. So I go here, I find C2H4, which I see right here, ethene. I see its standard state as a gas. Great. Delta H of formation is 52, positive 52.0 kilojoules per mole. The kilojoules per mole is when I'm worrying about making 1 mole of the compound. Once I combine all of my delta H's together, it won't be per mole of anything. So I can just call that kilojoules. That was probably a little confusing what I just said. Just know that these are standard enthalpies for forming each of these compounds. Again, once we put it into the equation to find the delta H of the overall reaction, your answer isn't going to be per mole because there's nothing defined as per mole of what. So you'll just have kilojoules. HCl, how would I make HCl? Well, if I'm doing formation, I need to make exactly 1 mole of HCl. So how would I make 1 mole of HCl? 1/2 H2 plus 1/2 Cl2. Why did I need to make those 1/2? Because I needed 1 mole of HCl. Hydrogen and chlorine are both diatomic, so their elemental states are H2 and Cl2. So to get just one of each of those atoms to make HCl, I needed those half coefficients. On a paper 2 style problem, you wouldn't necessarily need to write this intermediate, but they could absolutely ask you as a multiple choice, what does the delta H of formation look like for HCl? And we actually saw that in our check for understanding, not for HCl, but for another molecule. All right, so I'm going to look up the delta H of formation. Let me just make sure I'm labeling these really clearly. Equals HCl. The acids are down at the bottom here. HCl, negative 92.3 kilojoules. Beautiful. And now I have C2H5Cl. All right, how would I form that? Well, I need 2 C's plus 3/2 H2s. Sorry, not 3/2, 5/2. Getting it to balance. 1/2 Cl2 yields 1. It has to be 1 by definition because it's delta H of formation for C2H5Cl. And I should be able to find that. C2H5Cl is right here, negative delta H of formation. The standard enthalpy of formation for this molecule is negative 137 kilojoules. All right, let's grab another piece of paper here. Oops, okay. All right, so now I just have a pretty simple Hess's law problem. I'm going to write my overall reaction C2H4 plus HCl yields C2H5Cl. Okay, so looking at my first intermediate reaction, I see that the molecule I want has the correct coefficient. It's the same coefficient in the overall reaction, but it's going the wrong way. So let me rewrite this. Plus 2C plus 2H2. Delta H is equal to negative 52 there. My second intermediate, again, is going the wrong way. So to match up with the overall reaction, so I'm going to need to reverse that one as well. HCl yields 1/2 H2 plus 1/2 Cl2. Delta H is now positive 92.3. Great. C2H5Cl, that's going in exactly the right way. 2C plus 5/2 H2 plus 1/2 Cl2 is C2H5Cl. Delta H is equal to negative 137 kilojoules. I didn't need to reverse or change coefficients because I have all 1 coefficients here. It is balanced, and this last one was going the right way. So just to remind myself, here I had delta H formation for my reactant in my overall equation. Here I also delta H formation for my reactant in my overall equation. And this was delta H formation of my product in my overall equation. All right, so then I'm just going to combine them together. Negative 52 plus 92.3 minus 137. And you're just going to put that into your calculator. The second example, and this one we didn't have time for in class, this is doing exactly the same thing. So you can have an overall equation that is, for example, a combustion reaction. It doesn't really matter what type of reaction the overall equation is. You would do the same thing here. You would find delta H So in this case, C3H8, propane, negative 105, delta H of formation here is 0 because elemental oxygen. CO2, right here, carbon dioxide, negative 393.5, negative 393.5, H2O, great, and H2O gas, so I have steam. Oh, okay. H2O steam is negative 241.8, negative 241.8. So in order to show full work, I think the intermediates are helpful, but it is true. This is delta HF. Okay. But we can see what had to happen is that all of the delta H of the reactants, we had to flip that sign, and the products we did not. So I can also just directly from this data I pulled from the data booklet, I can get my delta H for this reaction. Again, it's a combustion reaction, but that doesn't really matter because I'm using formation data in order to theoretically find the enthalpy change for this reaction. Of course, I could also use Q equals MC delta T. I could also do this experimentally and then compare with formation data, compare with bond enthalpy data. So delta H for the reaction is, I know that because these are in the reactants, I'm going to have to flip that sign. So I'm going to have to make it negative, that negative 105 plus 0, or 5 times 0, which will still be 0, plus, here's my formation for 1 mole of CO2. So 3 moles of CO2. I'm going to run out of space here. Let's move this over. 3 moles of CO2 is negative 393.5. 4 moles of water plus 4 moles of negative 241.8. Notice that I did not flip these signs because this here is in the products. All right, and then you'll just put that into your calculator. So we can summarize this by looking at the formation data. We can add the delta H of formation for the products, subtract the reactants. We just prove that to ourselves by looking at the intermediates and seeing how we have to flip the sign. All right, if you have questions at this point in the video, you can stop, pause, add to the question document, and let's move along. Enthalpy of combustion. Enthalpy of combustion. Enthalpy of combustion is when 1 mole of a substance is burned completely under standard conditions. Where do you see this data? Section 13. So let's go ahead, move along to section 13. All right, so same idea. We have an equation. This happens to be the equation for the formation of methane, of CH4. Again, it doesn't really matter what equation it is. But what I'm going to do is I'm going to use the delta H of combustion for each of these things, the delta H of combustion for each of these things to find the overall enthalpy for a reaction, for this reaction. So very similar idea to before. But instead of using formation data, I'm now looking at combustion data. CH, oops, I forgot the H there. CH4 gas. All right, so my intermediates. Carbon, when I write combustion intermediates, remember combustion is in oxygen. This must be the 1 mole. CO2, and I looked that up. See, carbon by itself is negative 394 kilojoules per mole of individual carbon. H2, when I write this as an intermediate, this by definition needs to be 1, the enthalpy of combustion. plus oxygen yields H2O. And of course the H2O we can find, I believe it is down, oh, it's H2. Yep, H2 is right here, negative 286. So delta H combustion is negative 286, the combustion for H2. And then CH4 should be right here. Methane is negative 891. So CH4 plus oxygen yields CO2 plus H2O, just the complete combustion of methane, as you remember from organic. That enthalpy of combustion is negative 891. All right, so again, now we just have Hess's law. I see that my first intermediate matches up in terms of the both the coefficient and where carbon is. So delta H of my overall reaction, again, it happens to be a formation reaction. You could use different types of reactions. It doesn't really matter that it's formation. The delta H of the reaction, I'm going to take that 394 that I'm getting from the combustion of just carbon plus H2 here. I have two H2s, so plus 2 times negative 286. So let me cross off what I've done. So this one I put here. This one, the combustion of H2, I put right here. I see that I did not have to flip anything. And now let's look at CH4. Well, in my overall reaction, CH4 is in the products. In the intermediate that I wrote, using combustion data, CH4 is in the reactants. So I'm going to need to flip this reaction and make this positive. So I'm adding 891. And I'm going to put this number into my calculator. I trust that you can do that. So I'm not actually showing you the math in this video. I trust you know how to use your calculator. Your final answer will be in kilojoules. We can summarize these by taking the delta H of combustion for the reactants. Of course, we need to include coefficients and subtract the delta H of combustion for the products. Of course, remembering to include coefficients. That's if we're using combustion data. We just saw that. The product, I see I had to flip that sign, which I'm showing here, because of how we write out combustion, the standard enthalpy of combustion. And then same thing down here with formation, except we saw based on the definition of standard enthalpy of formation, the ones that need to flip are reactants. So I hope that helps. We're really focused on trying to understand why these are the case. And you do need to understand the definitions of standard enthalpy of combustion and standard enthalpy of formation, because you could be asked to use them to find delta H for some reaction, or you could also be asked to come up with a standard enthalpy of combustion for one particular thing, or the standard enthalpy of combustion of formation, the standard enthalpy of formation for just one particular molecule. All right, I hope that helps. Feel free to ask me as many questions as you have, send them in the question document, tag me in your documents. You've got this. I believe in you.